Welcome to this explainer. Today, we're diving into the absolute backbone of the internet. If you're a total newbie to networking, you've probably heard folks throw around the term OSI model. Maybe you've even tried to memorize its layers like a boring grocery list. Well, scratch that. Today, we're shifting our mindset from rote memorization to figuring out the actual real-world problems this model solves. By the end of this, you won't just know the layers, you're going to understand exactly why they exist in the first place.
To really get networking, we've got to start with the most basic problem it solves. Imagine this. You've got a file on computer A, and you desperately need it on computer B, right across the room. Without a network, you'd physically, and yeah, frustratingly, walk a USB drive over. But figuring out how to do that automatically, not just across the room, but instantly across the entire globe, that's literally the whole reason computer networking exists.
As a senior engineer recently pointed out in our source materials, the real secret here is to stop memorizing layers and start understanding what specific problem each layer actually fixes. Seriously, take a deep breath and let go of the flashcards. Think of the OSI model as just a handy mental framework. It tracks how your data moves from your laptop all the way to some massive server farm and right back again.
Okay, here's our roadmap for today. We'll hit 1. The problem networking solves. 2. Moving data, layers 1 and 2. 3. End-to-end delivery, layers 3 and 4. 4. The application, layers 5 to 7. 5. Real-world cloud and security. And finally 6. The quantum OSI future. Let's get into it.
Section 1. The problem networking solves.
Before we start climbing the stack, we need to know where this thing actually came from. Picture the 1970s. Computers were just starting to connect, but there was a massive headache. Equipment from vendor A literally couldn't talk to equipment from vendor B. It was a total digital Tower of Babel. So, the International Organization for Standardization, the ISO, stepped in and developed the Open Systems Interconnection, or OSI, model. Yeah, they basically just flipped the letters around. By chopping up all that massive network complexity into 7 self-contained layers, vendors could finally build hardware and software that universally understood each other. A real game changer.
Section 2. Moving data. Let's look at layers 1 and 2. All right, let's start at the very bottom, where abstract data turns into physical reality. Welcome to Layer 1, the physical layer. When you strip it all away, computer data is just ones and zeros, right? Raw bits? Well, Layer's only job is to physically transport those bits from point A to point B. And what's kind of wild here is that physical is a pretty broad term. Whether you're using a tangible copper Ethernet cable, a fiber optic line, or totally invisible Wi-Fi radio waves, it all lives right here at Layer 1. It only cares about the transport medium.
So moving up, let's see how this builds into Layer 2, the data link layer. Layer 1 moves the bits, sure, but how do they find the right local machine? Well, Layer 2 handles local, hop-to-hop delivery using physical MAC addresses. These are baked right into your network card. You can think of a MAC address like your computer's social security number. It's physical, it's permanent. But a MAC address only gets you to the very next jump, like your home router. To get across the globe, we need Layer 3, which brings in IP addresses. Your IP is way more like your mailing address. It stays constant for the entire end-to-end journey.
Section 3. End-to-end delivery, layers 3 and 4.
So once your data leaves your cozy home or office network, we need a way to route it across the wild global internet. Enter Layer 3, the network layer. Layer 3 basically acts like the global postal service of the internet. It relies on routers and those 32-bit IP addresses we just talked about to make sure your packet finds its final destination, jumping across all sorts of different networks. Whenever you type in a website, it's Layer 3 that's navigating the giant maze of global routers to find the absolute best path for your data.
But hold on, here is a fascinating little mystery for you to think about. Your computer is probably running a web browser, Spotify, maybe an email client, and Zoom, all at the exact same time. And they are all sharing the exact same IP address. So, when a data packet arrives at your machine, how do we avoid a totally chaotic mix-up? Like, how do we make sure your web browser doesn't accidentally try to play your Zoom video feed?
That's where Layer 4 comes in. The transport layer perfectly solves that chaos by distinguishing between different data streams using specific things called ports. Let's break it down. Think of your IP address as an entire apartment building, and the port is the specific apartment number. Secure web traffic always goes to port 443. Email goes somewhere else. Layer 4 also uses protocols like TCP, which is like certified mail, ensuring every single piece arrives perfectly ordered, and UDP, which is more like a lightning-fast postcard. UDP is great for things like live video, where speed is way more important than absolute perfection.
Section 4. The application. Let's look at layers 5 to 7.
Okay, we've built the physical connection, routed our data globally, and sorted it all by application. Now we finally reach the top of the stack. This is where you, the user, and the software actually step into the picture. Now, the textbook OSI model defines distinct session, presentation, and application layers. But honestly, in real-world modern networking, these top three are almost always grouped together. Layer 5 opens and maintains your sessions. Layer 6 is busy formatting and encrypting your data, like securing your credit card with SSL. And finally, Layer 7 is where protocols like HTTP actually serve up the web pages you're clicking on.
So how does this entire stack function together as one unit? Through a super important process called encapsulation. It's basically like a giant Russian nesting doll. To actually send a message, your app data gets wrapped or encapsulated in a brand new header at every single layer as it travels down your computer stack. Your web request gets wrapped with a port at layer 4, then an IP address at layer 3, and a MAC address at layer 2, before finally being blasted out as raw bits at layer 1. And when it arrives at its destination, the receiving computer just does it in reverse. It climbs up the stack, unwrapping the data layer by layer until the application can finally read it.
Moving on to Section 5, Real-World Cloud and Security.
So why does all of this actually matter to a networking newbie today? Let's pull this right out of the textbook and apply it to modern cloud architecture. Take a look at this table. Notice how AWS services and firewall types map absolutely perfectly to the layers we just learned? For instance, a Layer 3 firewall only understands in blocks IP addresses, but a Layer 7 firewall? That one is smart enough to look deep inside the data and block specific applications, like YouTube or maybe malware. Over in AWS, your virtual private cloud operates at Layer 3, your security groups are managing Layer 4 ports, and an application load balancer routes traffic at Layer 7. Once you grasp this framework, cloud engineering literally just clicks into place.
And finally, Section 6, the Quantum OSI Future.
All right, now that you've got a solid grip on the classic 7-layer model, I'm going to intentionally break it for you. See, the future of networking is quantum, and quantum physics simply does not play by the old OSI rules. Our classic model relies completely on the ability to duplicate, buffer, and retransmit dropped packets. But in quantum networking, there's a wild principle called the no-cloning theorem. It means you physically cannot copy quantum data without instantly destroying it. So you absolutely cannot use traditional error correction or routing when your data literally can't be copied. Mind-blowing, right?
To get around this, researchers are actually proposing an expanded 9-layer quantum converged stack. They're adding a brand new layer 0 at the very bottom just to handle the incredibly weird physics of quantum entanglement and teleportation. And then at the very top, they're adding a layer 8, an AI and LLM-driven cognitive intent plane to orchestrate this wildly complex probabilistic network in real time.
Which brings us to the ultimate question for you to take away today. As quantum mechanics literally rewrite the physical rules of how data exists, is this classic 7-layer model going to adapt and survive? Or are we witnessing the birth of a completely new networking universe? The foundation you've learned today is absolutely crucial for understanding today's internet, but keep your eyes peeled, because the future of how data flows is still being invented. Thanks for joining me for this explainer, and keep questioning how our world connects.